Okay, here are our last 5 multiple choice questions for the 2019 Regents. The first question we're going to look at in this video is actually one of my favorite questions or favorite types of questions that can be asked, especially in the modern physics unit. I think this is a really interesting question. It leads to a lot of interesting things in modern physics and actually quantum mechanics if you ever go on to take a course like that. A red photon in the bright line spectrum of hydrogen gas has an energy of 3.02 times 10 to the negative 19th joules. What energy level transition does an electron in the hydrogen atom undergo to produce this photon? So what we're being asked here is we are being asked to determine there's a certain amount of energy that gets released with this photon being released from an atom, from an electron moving from one energy level down to the next. What was the initial energy level? What was the final energy level? So we're going to be looking at hydrogen. We want to know where the electron started off and where it ended up in order to release this much energy. Now, one thing that you need to look at, this is kind of the reverse of how I normally teach this problem. The energy on this chart is in EV. We are told the energy of this photon, this red photon, and we're told the energy, if this thing goes away, we are told the energy in joules. First thing we need to do, if we want to find the energy levels, we need to convert this into, electron volts. We can do this using the conversion on the front of the reference table. I'm just going to kind of write it down here. 1.6 times 10 to the negative 19th joules is 1 EV. And it turns out that this amount of energy in electron volts is about 1.8875 EV. And you know what, I'm going to round that to 1.89 EV. Because if you notice on our energy level diagram here, we have 2 decimal places, so I might as well go with 2 decimal places here. Now what we need to do is we have, n equals 3 to n equals 2, n equals 4 to n equals 2, n equals 5 to n equals 2, n equals 6 to n equals 2. And this might seem kind of intimidating, but we could probably use some logic to figure this out. Which one? We need to find the difference in energy levels that corresponds to this much energy, because as that electron falls from one energy level to the next, it will release some energy. It's moving to a lower energy state. It's got to do something with that energy. It releases or emits a photon. It emits a photon with this much energy, and that energy corresponds to the difference in energy level. So if we find the difference in energy level of this much, that is our answer. So let's go to, let's just go to the first one, n equals 3 to n equals 2. The n equals 3 state is negative 1.51. The n equals 2 state is negative 3.40. So let's see what happens. We start off at negative 1.51 EV. And then it loses energy, so we're going to subtract minus 3.40. And lo and behold, this becomes addition, but it works out to 1.89 EV. So there's a difference of 1.89 EV between these 2 energy levels. So that just means our answer to this one is number 1. All of these other ones with higher energy levels going down to n equals 2 would mean that more energy is released. Okay? So you probably could have gotten the same thing by figuring, okay, let's try this one first. Oh, it doesn't work. This is too much energy. Oh, it must be the lower energy level. So there's a number of ways you could have done this. But anyways, the math works out to choice number 1. We have this much, this difference in energy level results in this much energy being released with this photon, which actually also means that it becomes, that it is a red photon. That's how we perceive it. Interesting question, a little bit different from normal. All right, let's move on to 47. In the diagram below, a negatively charged rod is placed between but does not touch identical small metal spheres R and S hanging from insulating threads. So this is negative. What can be concluded if the rod repels R but attracts sphere S? Okay, let's worry about R first. What do we know about repulsion and the electrostatic force? It happens with like charges, okay? So R must be negative, okay? R being positive, that doesn't make any sense. The only distinction between these two is if S is positive or neutral. We know that opposite charges attract. So it's definitely true that S could be positive, could it also be neutral? Okay, does neutral get attracted to a charge? And the answer is it actually does. What happens is the object becomes polarized, and it is very slightly attracted. The neutral object becomes polarized to some degree, and it actually does attract or get attracted to our charged object. So the answer here is actually number 2, which can be a little tricky. But we made this table in our notes during the year that showed that neutral objects are attracted to charged objects. Another way you can see this is take a balloon, rub it on yourself, or rub it on something, I guess not yourself, rub it on something to get the balloon charged, and then hold it up next to your hair. Your hair will go towards it even if it's not, well, I don't have much hair right now, but your hair will go towards it even though you are neutral, your hair is neutral. Okay, your hair is neutral, it's getting attracted to that charged balloon, the hair is polarizing, and it is still attracted to it. That's an example you can remember. So the answer to 47 is number 2. Okay, another great question. The amount of electric energy consumed by a 60-watt light bulb, 60 watts would be the power, for 1 minute. Now what should we do here? Okay, 1 minute, we don't typically use minutes. We should really convert this to a time of 60 seconds. The amount of electric energy consumed by a 60-watt light bulb for 1 minute could lift a 10 Newton object. Very similarly to before, if it says a 10 Newton object, it's telling you the weight, which means it's telling you the mass multiplied by g, the acceleration due to gravity. A 10 Newton object to a maximum height of what? We're looking for h. How high can this object be lifted in essentially 60 seconds? So it's a little interesting. We're talking about the energy that a light bulb produces. Okay? If we were to take that energy and convert it into mechanical energy or gravitational potential energy, how high could we get this object? So we've actually got a little bit of work to do for this question. The first thing that we have to do, let's worry about the light bulb first, okay? We know that the light bulb, we know the power of the light bulb, we know the time that it's in operation for, so we can determine the work that that light bulb does. In other words, how much energy it puts out. It turns out that if we have 60-watt light bulb shining for 60 seconds, the energy, or in other words, that it puts out, or the work that it does, is 3,600 joules. Now, what do we want to do with that energy? We want to lift this object up. So, we want to do some work to change the gravitational potential energy of an object. And if we're changing the gravitational potential energy, that means we are changing the height. We want to lift it up to some height, assuming it starts at the ground. Okay? So we're going to assume the initial height is 0, and then we're going to plug in the work done, the energy that that light bulb gave off, if we were able to turn that into gravitational potential energy somehow. That'd be kind of cool, have a light bulb turn on and it brings something up. 3,600 joules equals, let's see, our 10 Newton object. That's our mg that we just plugged in for, and we're solving for the final height. We get that the final height must be 360 meters. That's really, really big, okay? 360 meters is like the height of a skyscraper. Probably almost a little bit higher. Or, well, yeah, the height of a skyscraper approximately. So a 60-watt light bulb operating for a minute is giving off that much energy to lift. Granted, this is a very light object, about 1 kilogram or so. But to lift that up to the height of a skyscraper, that's a decent amount of energy. That's very interesting. Nice calculational question that relates electrical energy to mechanical energy. We actually had a question just like that on the AP exam. 49. Microwaves can have a wavelength closest to. This is our standard estimate the size of something question. So, we talk about microwaves. Let's go to the chart that shows us the size of microwaves. Right up here, microwaves extend from 10 to the -4th meters up to 10 to the 0 meters. So that means they extend from 1 meter down to approximately, let me see if I do this right. I don't think that's right, hold on. There we go. Microwaves extend in, they could have a range between 0.0001 meter up to 1 meter. We need something that's between those. 1 meter, as you all know, of course I grab a half meter. 1 meter is one of these things. Okay, this is a meter. 0.0001 meter, you see the little tiny lines that are well, you can't see them, but they're millimeters on here? Think a tenth of one of those. Which one of these objects is between those ranges of a meter down to a tenth of a millimeter? Radius of Earth? I don't think so. Height of Mount Everest? Still no. Length of a football field? Not even close. Length of a physics student's thumb? Definitely bigger than a tenth of a millimeter, definitely smaller than a meter. Microwaves could be about this size. Absolutely. Last multiple choice question, a good interference question. Okay? Good superposition interference question. We have two pulses approaching each other in a uniform medium as represented by the diagram below. Which diagram best represents the superposition of the two pulses when they overlap? Now the thing to remember with this is that when two pulses are overlapping, you simply have to add the displacements at each point that will give you the shape. So it takes a little bit of practice, but here is what these two pulses would look like. Or let's draw out, let's just trace the two pulses superimposed on the top of each other. Here's the pulse on the left. Oh, I'm drawing this in the exact wrong spot for you guys. Sorry. Let's bring it over here. Okay, there we go. I'm leaving this space in the middle so that we can draw the two shapes. The shape that's on the left might look like this, okay? If I take that trace and I bring it down. Trace on the right would look something like this, okay? Now we have to figure out what the pulse would look like, what the overall pulse would look like when these two are overlapped. So let's look at the left edge. The pulse that's originally on the left has a height of 0 at its left edge. This has a negative displacement. So we know that if we're going to add the displacements together at each point, the wave should start down here like this. Same thing on the right edge. Right edge of the left-hand pulse has a positive displacement. This has a displacement of 0. So the height at this edge should just be the height up here. We know that, let's say, halfway in between, this one has a, I could make up numbers, but halfway through the pulse, this has this much height, and this one has a height of about this. These are going to cancel each other out, right? One's a positive displacement, the other is a negative displacement. So halfway through, we should get a displacement of 0. And that can kind of tell us what the shape overall should look like. We have straight lines here. It's not too big of a stretch to assume that we should have a straight line from the beginning of the pulse to the end of the pulse. What we're going to end up with is actually a line that looks somewhat like this. Okay? This is the actual shape that gets combined, and this is actually one of the trickiest questions I've seen them do yet as far as interference and superposition goes. But the idea is you simply add the displacements at each point. And I could make a whole bunch more points. If I had graph paper, this would be a perfect question to do. I don't have that sort of time though, okay? You should get good at being able to kind of look at this, to sketch out what maybe the important points should look like the left-hand side, right-hand side, maybe in the middle, and then kind of saying, okay, well maybe there's, it seems like the rates of change of the shapes here, in other words, the slopes of these pulses are pretty even, you know, they're constant slopes. So that kind of leads you to think, okay, well at this point where they're perfectly overlapped, perhaps it's also a constant slope. It just ends up being very, very steep compared to those two, twice as steep it looks like. The answer to that is number 1. We did do a lot of practice, or at least a couple days of practice with that in our waves unit. That is the multiple choice section. I'll be moving into the short answer section now. Do a couple more videos for those, and then we'll be all done.